All right, hello guys. Hope you guys had a great weekend and had some time to refresh yourself. This is the second week of the new semester, so it's time to get back to work. And as I mentioned in the course website, I'm planning to cover 3 topics on consumer theory this week. First, utility maximization, and second, expenditure minimization, and third, the relationship, the so-called duality. Okay, so I'm not 100% sure if I can cover these 3 topics all together this week, but yeah, let me do my best much as possible. Okay. So in the previous week, we talked about basic elements in the framework about consumer theory. So we talked about the bundle. So bundle indicates consumer choice in market, and the consumption set, the set of all feasible bundles, and budget constraint, the set of all affordable bundles, and finally preference relations. Okay? And I introduced several standard conditions made on preference relations, from rationality to convexity assumptions. All right, so rationality and continuity are necessary condition for existence of utility function. So we also talked about utility representation theorem. So as long as preference relation, so it turns out that as long as preference relation is rational and continuous, we can guarantee existence of nice utility function. So we don't have to work with a L-dimensional consumption bundle. Instead, we can work with real valued utility function. All right, and then we also talked about 2 more assumptions on preference relation, desirability assumptions such as monotonicity or local non-satiation. So the more the better. Okay, and then finally we talked about convexity assumption, which is concerned about the exchange rate between 2 commodities. In other words, marginal rate of substitution. Okay. So with that background in hand, now we initiate our study of consumer behavior in market by tackling on utility maximization problem. All right, so let me go to slide page number 30, where we have a utility maximization problem. So from now on, we are going to assume that preference relation is rational and continuous. Okay? So we can make sure the existence of utility function, and that is continuous. Okay, continuously, if we assume monotonicity, it is a continuously increasing function. All right, and there are 2 underlying assumptions, as I mentioned in the previous week. So we assume the market completeness. Okay, so as soon as the consumer participates in the market, she can observe the price information. Okay, so the price information is publicly available, and the price vector P is independently determined by individual behavior. Okay, rather it is determined by aggregate demand or supply. All right, so under those assumptions, it is natural to think that consumer is willing to choose one bundle so as to maximize her utility. Okay? So that brings us to the following optimization problem. Okay, so this is called the UMP, utility maximization problem. So she wants to choose one bundle X, okay, so as to maximize utility. Okay, and bundle X must be feasible. So it should be an element of the consumption set X. And furthermore, it should be affordable. Okay, so the total expenditure for choosing bundle X cannot exceed the consumer's wealth. Okay, so that is a one optimization problem, given constraint, given budget constraint, and then we can rewrite this optimization problem in a succinct form using the budget set. Okay, remember the budget set B depends on 2 parameters, price vector P and W. Okay, so there is a set of all bundles satisfying this inequality. Okay, so using that set B, we can rewrite this maximize u of x, where x is an element of set B. Yeah. All right, so in this video, I'm going to talk about how to solve this and what is the main property of the solution. Yeah. All right. And then the first result we can derive from the problem is existence of a solution. Okay. So the first result tells us if the price vector P is a strictly positive. Okay, so double inequality means the price of every commodity is a strictly positive. So there is a no free good in the market. And U is continuous, function U is continuous. Okay, so that is implied by the assumption of continuity. Okay? Then the problem U and P has at least one solution. Okay, and it is immediate from the so-called extreme value theorem in mathematics. And this theorem states that, extreme value theorem states that, if we have a continuous function, okay, so the graph of the function is well connected like this, and defined over a compact set. So if function f depends on just a single variable, compact set means, closed and bounded interval, say from A to B. Okay, so over this interval, the graph of the function is well connected like this. All right, and then the theorem states that, the function f, so as long as, function f is continuous and defined over compact set, then there is some point in that interval where the function attains the global max, and another point in that interval, so in the compact set, where the function attains the global mean. Okay, so that is quite intuitive from this figure, and the general statement of extreme value theorem tells us, the general statement is, suppose that we have function f is a mapping from set x to y. Okay, and it is continuous. All right, and then we define set K as a subset of X, subset of the domain, and it's a compact set. All right, then f of K, all right, so the image of this function over the set K is also compact. Compact. Okay, so bounded and closed. Bounded and closed. All right, so meaning that supremum and infimum of this image exist. Okay, in other words, if we attempt to maximize or minimize this function, global mean and global max or global mean exist. Okay, so the extreme value theorem guarantees the existence of a solution to optimization problem where we want to maximize a continuous function over some compact set. Okay, and going back to U and P, we know function U is continuous. That is implied by the continuity assumption, and the domain of this function, okay, originally that is x, but in the end we have to choose one bundle inside the compact set budget set. Okay, we know the budget set is compact as long as price vector is strictly positive. So by the extreme value theorem, existence of a solution follows. And then we are going to denote by x star the set of solutions to the U and P. Okay, so at x star, function U is a maximized. So argmax denotes the solution to optimization problem. Okay, so at this point, x star, function U is going to be maximized. Okay, and in economics, it is called the Walrasian demand. Okay, and observe that Walrasian demand will depend on price vector P and consumer's income W. All right, and those two are observable okay? Not just by this consumer, but by the analyst, okay? By economist, right? And we can see what consumer choose in the market, okay, using data. So this Walrasian demand has a one merit that is a observable, okay? Because it depends on two observable parameters. All right, and then so one more thing you have to notice is, this Walrasian demand is not necessarily single valued. Okay, think about this example, where we have indifference curve and Budget line. And if you took undergraduate microeconomics, you may have learned, at the optimal bundle we have a tangent condition. So at the optimal bundle, Budget line is tangent to the indifference curve. Yeah, so that brings us the the simple condition that marginal rate of substitution is equal to the relative price in case of two commodities. And now we are going to attempt to, so we are going to generalize that that simple result from the two commodity space. So by the way, if the indifference curve has some region, tangent to, so not just a single point, but we have some region where it is totally overlapped with the Budget line. Okay, then every bundle in this region is going to be optimal. Okay, so that is a Walrasian demand. Okay, so this it's not necessarily a single. So we don't have to have just a single solution. So in that exception, so in those some exceptional cases, we may have a multi-valued Walrasian demand. Another example of multi-valued Walrasian demand appears in the context of perfect substitute. Okay, remember, so if we have a linear utility, say 2x1 plus x2, and then budget constraint 2x1 plus x2 is more than 10. Yeah. In such a case, MRS is a fixed, right? Fixed by a constant 2. And then P1 over P2 relative price is also 2. Okay. In such a case, Budget line is totally overlapped by one indifference curve. So every bundle on the Budget line, every bundle on the Budget line, is going to be optimal. Okay? So we have a set of solutions to the UMP, right? So in such a case, we say that so X star is Walrasian demand correspondence, okay, multi-valued function, right? But if we have a single solution to the UMP, so X star is a single valued, we have just one bundle where the utility is maximized given budget constraint, then we say X star is Walrasian demand function. Okay. All right, and then I first enumerate the general properties of Walrasian demand. Okay. In the next slide. So suppose that preference relation satisfies the three basic assumptions: rationality, so completeness, transitivity, and continuity. Okay, and plus one desirability assumption, local non-satiation. All right, and the Walrasian demand possesses the following properties. The first property is homogeneous of degree 0 in the price vector and income. All right, so that simply means, so we have a Walrasian demand depends on P and W. Okay, and then we scale up each parameter by alpha. Okay, so we multiply each parameter by alpha, where alpha is a strictly positive constant. Okay? And we end up with X star, the original Walrasian demand. So X star of P and W. Okay? So we can simply remove that constant. Okay? The intuition is going back to the UMP. All right, so this is the original UMP, and the solution to this problem is denoted by X star, P and W. Okay. Now what is x star of alpha p and alpha w? Now, because if we take a look at the objective function, it does not depend on p and w, right? So still we have the same utility function, right? The only change occurs in the Basic constraint. Now the Basic constraint becomes alpha p after scaling up, alpha p dot x less than equal to or equal to alpha w. Okay, but alpha is a positive constant, so we can simply remove this constant from both sides without reversing the inequality. Okay, so it makes no difference, right? The problem with p and w is exactly the same as the problem with alpha p and alpha w. Okay? So the solution to this problem comes out, that is x star alpha p and alpha w is exactly the same as the original solution, the solution to the original problem. Okay? And so we have homogeneity of degree 0. Okay? And the second property states that Walras law. So Walras law states that p dot x should be equal to w. Okay? Where x is an element of Walrasian demand. Okay? So it simply says if if x is a optimal bundle, then all income should be exhausted. The Walras law states that all disposable income must be exhausted. In other words, the Basic constraint must be binding at the optimum. Yeah. So the original Basic constraint was inequality p dot x is less than or equal to w. Okay, but if x is chosen as a optimal bundle, okay, the Walrasian demand, then so the inequality becomes equality. Yeah? So the Basic constraint holds with an equality. Right? We usually say in a constraint, the given constraint is a binding in this case. All right, so that is one simple implication of desirability assumption. Okay, so I guess if you took undergraduate microeconomics, you may have learned under monotonicity, so the more the better, then at the optimal bundle. So the optimal bundle must be on the budget line. Okay, but it turns out that we can relax that assumption monotonicity to local non-satiation. So the proof is immediate. That is a proof by contradiction. Okay, and suppose that optimal bundle is not on the budget line, instead is inside the triangle. Okay, so suppose that this x inside the triangle. So at this bundle, Basic constraint will be held with inequality, strict inequality. All right, then by local non-satiation, we can the alternative bundle y in the neighborhood of x, which is strictly better than x. Okay, and this preference of this utility function u represents the given preference relation. So that simply means u of y is strictly higher than u of x. Okay, and this neighborhood is a very small neighborhood of x. Okay, so still this bundle y is inside this triangle, so that is affordable. Okay, so the consumer can choose this bundle given price and given income. All right, and furthermore, by choosing this bundle, consumer can enjoy higher level of utility. So that is a contradiction with our presumption that x is the optimal bundle. Okay, so because y gives the consumer higher level of utility, so that contradicts that x is the optimal bundle. right? And that contradiction gives us the Wallace law. Okay? So if X is an optimal bundle, Bose constraint must be binding at that optimum. All right, and then the third property is convexity and uniqueness. So under the assumption that preference relation is convex, Walrasian demand is a convex set. Okay? That means, suppose that we have this indifference curve, okay? And this is the Gaussian line, right? So we have two optimal bundles, say X and X prime. So bundle X is optimum. So that is an element of the Walrasian demand. And so is X prime. Then, convexity implies any average bundle. So the consumer wants to mix these two bundles with weight alpha, right? And that is also optimal bundle. Okay? So it is consistent with the definition of a convex set. So with the definition that X star is a convex set. Okay? If we have one element and another element, then any average of that weighted average is also an element of the set. All right, and then that is immediate from the definition of convexity assumption. Okay, remember, if the preference relation is convex, we know that function u representing this preference relation is quasi-concave. Right? And quasi-concavity in turn implies upper contour set is convex. So set of bundles where u of x is larger than or equal to some constant u star, so can be regarded as a one upper contour set of this function u is convex. Okay. All right. So suppose that X is, so this is what we want to show. So we want to show that X star is a convex set. Okay. And we assume X is an optimal bundle. All right. And then the highest level of utility obtainable at this by choosing this optimal bundle is given by U star. In other words, the level of this indifference curve is given by U star. Okay, so by choosing U, consumer can enjoy utility U star, and X prime is also another optimal bundle. So at that bundle, the level of utility is the same as before. All right. So that simply means this X and X prime are elements of this upper contour set, right? Because this upper contour set allows the equality. So let me call this UC, upper contour set. Then X and X prime belong to this set. All right. And we know that set UC is a convex set, okay? So any average bundle alpha x plus 1 minus alpha x prime is also an element of UC, okay? That means U of alpha x plus 1 minus alpha x prime will be higher than or equal to U star, okay? Because this bundle is an element of this set. Yeah, so it gives the consumer, at least this level of utility. All right, and then furthermore, this average bundle is affordable, right? Because a budget set is convex set. So X is one element of a budget set, so is X prime, and so is the average bundle, any average bundle between these two. Okay, so we assume that X and X prime are optimal bundles. So the level of utility by choosing this bundle is at most U star. So we can see that this is also, so U of this, utility from this average bundle is exactly equal to U star. Okay, that simply means this average bundle is also, that average bundle gives the consumer the same level of utility from the bundle X and X prime, so that is also optimal. Okay. And then under the more restrictive assumption, say preference relation is strictly convex. Okay, so if the preference relation is strictly convex, then function U becomes strictly quasi-concave. So now we have a strictly convex indifference curve toward the origin like this. Okay, so previously we have a convex set as a Walrasian demand, because indifference curve has that kind of region where which is parallel to Gaussian line, right? But in case of a strictly convex indifference curve, that kills out this kind of possibility, right? So we end up with just one single bundle, say X double prime, where the indifference curve is tangent to the Gaussian line. So we end up with just a single element. Okay? So if the preference relation is strictly convex, then Walrasian demand has just a single valued. So we have a Walrasian demand function. Okay? All right. And then in the next slide, so I'm going to briefly illustrate the way to solve this UMP. Okay? Usually we adopt the method of Lagrange multipliers. So that gives us a necessary condition for the solution to one optimization problem. Okay, so I want to highlight this is simply necessary condition for a solution to the following UMP. Okay, just like so if we have, so in case of a single variable function, zero derivative, this is not a sufficient condition, but rather it is a necessary condition, right? Because we want to maximize this function f. Okay, but if the function is concave downward like this, and so at this point the function has a zero derivative, but the function is minimized rather than maximized. Okay, so but this is why we have to check the second order derivative, right? Right, so just as zero derivative is just a necessary condition for the solution in case of a single variable function, for optimize, so the Lagrange multiplier is also a necessary condition for optimization problem, in given some constraints. All right, so the method tells us, suppose that X star is a solution to this UMP. All right, and X star is strictly positive. All right, so if we have just a two goods, so demand for good 1 and good 2, so that is a Walrasian demand, then this double inequality means every component is strictly positive. So demand for good 1 and demand for good 2 both are strictly positive. Okay, and we usually call this interior solution. An interior solution. So as a matter of fact, Lagrange multipliers gives us a necessary condition for an interior solution. Okay. All right. So we have one interior solution. All right. Then the following must be satisfied. There exists a lambda, non-negative. That is usually named the Lagrange multiplier associated with this logic constraint, at which interior solution, so the candidate, becomes a stationary point of the function L, that is u of x plus this expression. So it is called a Lagrangian. Okay. So the way to set up the Lagrangian is, we first put the objective function we want to maximize or minimize, okay, and plus lambda, okay, and we put the Lagrangian multiplier, and then multiply by the given constraint, okay, and before substitution we have to manipulate the given constraint into this form. So w minus p dot x is larger than or equal to 0. Okay, so we change the given constraint into this form. Something is larger than or equal to 0. Okay, so we move this p dot x to the right hand side, rather instead of moving w to the left hand side. Okay, and then we take this form. So we take this constraint, this expression, and then put it in the Lagrangian like this. Okay, so that's the standard way of setting up the Lagrangian in case of optimization. All right, so x star must be a stationary point of this. That means the partial derivative in case of two goose, okay, partial derivative of this Lagrangian with respect to x1 and partial with respect to x2 are equal to 0. Okay, that is a stationary point. So where the function has a 0 derivative, right? And additionally, the interior solution and the Lagrangian multiplier satisfies the following equation. So the product of Lagrangian multiplier and this expression, so the portion of the basic constraint should be equal to 0. Okay, that is called complementary slackness condition. Complementary slackness condition. So this condition tells us because the product must be equal to 0. So if the basic constraint is not binding, it has a slack. So there is some money left behind. Okay. So this is hold. So the basic constraint holds with an inequality, strict inequality. Okay. So this is a strictly positive. All right. So in order to have a 0 product, then we can see Lagrangian multiplier must be equal to 0. Okay. And conversely, if the Lagrangian multiplier is strictly positive, remember lambda is strictly positive or equal to 0. Okay. So if lambda is strictly positive, then basic constraint must be binding. Okay. So in that complementary way, so there is some complementary relationship between Lagrangian multiplier and basic constraint. So this is why we call that complementary slackness condition. Okay. Yeah, I'm going to illustrate a little bit more about this Lagrangian multiplier in the live lecture today with this CS utility. All right. So in the meantime, if we adopt this stationary condition, okay, so at an interior solution, so if x star is an interior solution to the UMP, the derivative of the Lagrangian must be equal to 0. Okay, so that simply means if we take the partial derivative of this Lagrangian, u of x becomes the partial derivative of u with respect to x1. Okay, and lambda w is a constant, so that goes away, and then we are left with after derivative lambda times p1. Yeah, so because p dot x is p1 x1 plus p to x2. Okay, so we set it equal to 0, and the second condition. Okay, now take the partial with respect take the partial derivative of the Lagrangian with respect to x2, then now utility function becomes this guy, right? And minus lambda p2, right? And it has a special name, the derivative of utility. We call that marginal utility, measuring the increment of utility from consuming one more unit of good 1 and good 2. So mu1, marginal utility from good 1, stands for increment of utility by consuming one more unit of good 1, and mu2, we can give the same interpretation. All right, so the first condition requires mu1 equals lambda p1. Second condition requires mu2 equal to lambda p2. All right, and then we can collect them and express in a vector form. So vector of marginal utilities equals lambda times price vector p1 and p2. Okay, and as the marginal utility is simply the partial derivative of a utility function, so the vector on the left hand side is the collection of partial derivatives, and that is called the gradient in mathematics. So the left hand side is the gradient of u. Yeah, so that equals lambda times price vector p. All right, so let me just remind you of the definition of gradient. So if we have a function f depends on several variables from x1 to x sub l, then gradient of this function f usually denoted by this upside down triangle, and f as simply the collection of the partial derivative. So from partial with respect to x1 to partial with respect to x sub l. Yeah? So going back to this one, so mu is the partial derivative of a utility function. So we can simply rewrite this as gradient of u. Okay, and then right hand side we have some non-negative constant lambda times price vector. All right, so the last condition simply tells us gradient. So gradient indicates the direction in which the function is increasing at the largest rate. So gradient indicates the direction of steepest ascent. Okay, so we have a point x star here, and at this point the gradient indicates this direction. Okay, so that simply means if we go in this direction, so if we increase x1 and x2, at this ratio, the utility, or the consumer's utility, is increasing at the largest rate. Yeah, so that is a geometric interpretation of the gradient, right? And this direction is equal to the price vector. And remember, the price vector is the normal vector of this Gaussian line. Okay, so this vector p is perpendicular to this Gaussian line. Right? So the geometric interpretation of this condition derived from Lagrange multiplier simply tells us price vector and the gradient of utility indicates the same direction. All right, so this is why we have a tangents condition for optimal bundle. So at that bundle, Gaussian line and the indifference curve are tangent to each other. Right? And then the same condition can be extended to L commodity space. So in case of L commodities, we have a gradient, L dimensional vector. So from mu1 to mu_L, and we have a L dimensional price vector. Okay, so we have exactly the same condition after application of this Lagrange multiplier. Right? And then regarding Lagrange multiplier lambda, there is a nice interpretation. So multiplier can be understood as the marginal utility of income. Okay, the way to see this is think about this condition. Now we take this condition dividing by p1, then solving for lambda, we have mu1 over p1. Okay, and solving the second equation for lambda by dividing by p2, we have mu2 over p2. right? So the ratio of marginal utility to the price is called marginal utility from dollar. So this is named as mu per dollar. Okay. So yeah, let me illustrate that with a specific example. So suppose that mu1 is equal to 4. Okay, at some bundle. That means at the current bundle, if the consumer consumes one more unit of good one, he can effectively increase the level of utility by 4 units. Okay, so that is an interpretation of marginal utility, right? And suppose that price of this good is given by 2. Okay, then the marginal utility per dollar is going to be 2. 4 divided by 2. Okay, and this number 2 implies that if the consumer has one additional dollar, okay, then with that, consumer can purchase half a unit of good one, because the good one is traded at $2 in the market, right? And by purchasing that half unit, consumer can increase the utility, his utility, by 2 units. Okay, so the given basic constraint, the original basic constraint was this. Okay, and he wants to maximize his utility, right? And then suppose that he has additional $1, then his utility he can obtain is going to increase into utility, and that increment of utility is measured by Lagrange Multiplier. Okay? All right, so if lambda is equal to 2, then if he has additional $1, he can increase his utility by 2 units. Okay? So it can be thought of as the shadow cost, shadow value of $1. Yeah? So that's a standard way to interpret the Lagrange multiplier in optimization problems. All right, and there is another way to see this that is also important. So okay, if we think about the marginal utility from income, okay, and that is the derivative of the highest utility with respect to income. So suppose that we solve this optimization problem. Okay, we solve this, and then without +1. Okay, so x star is a function of P and W, right? And the highest level of utility he can attain is going to be this. Okay, and if we take this one and take the partial derivative with respect to income, so that gives us the increment of highest level of utility by having one more dollar. Okay, so that is a marginal utility from income. All right, so the way to compute this partial derivative is using the chain rule, because we have a composition, right? So we first take the partial with respect partial of u, the outer function. That gives us the gradient of u, and dot product. We multiply by the derivative of the inside. Okay, that is derivative of this x star with respect to w. Okay, so the chain rule. All right, and then we know that if x star is a Walrasian demand, then gradient of u is equal to lambda times p. All right, so this marginal utility per income, this is mu from income. All right, this is lambda p dot tw or dw of x star. This is a derivative, partial derivative of x star with respect to w. All right, and then okay, and we can show that this is simply lambda because Walrasian demand satisfies Walras law. So p dot x star is always equal to w. Okay, So we take this identity and compute the partial derivative with respect to w, then it's going to be partial with respect to w, and the right side becomes 1. Okay, so that means this guy is equal to 1. Okay, so lambda stands for marginal utility from income. All right, so in case of two goods, we can give an interpretation to lambda this way, but in case of many goods, using vector calculus, we can reach the we can draw the same conclusion. All right, and then in some cases, so remember, Lagrange multiplier gives us a necessary condition for interior solution. Okay, but after adopting that Lagrange multiplier, we may end up with a non-existence of lambda. For example, we want to solve, so we want to maximize this utility given the constraint 3x1 plus 2x2 is smaller than 10. All right, then mu1 is 2, that fixed marginal rate of MRS is 2. But P1 over P2 is 3/2, right? So never mind. So the first condition, I'm sorry about this. So the first condition for stationarity is mu1 2 equals lambda times P1 3, and the second condition requires mu2, which is 1, equal to lambda times 2, right? So you can easily check there is a no common lambda satisfying this system of equations. All right. In some other cases, we end up with negative demand, right? That does not make any sense. So in that case, we have to suspect the possibility of a corner solution. Yeah. So we can conclude there's a no interior solution because if there's a no candidate satisfying the Lagrange multiplier condition, so now we have to suspect the possibility of a corner solution. So corner solution implies that some element is equal to 0. So in case of two commodities, if we have this budget set, we have two candidates for a corner solution. Either this point where consumer decides not to consume the second good, and or this point where the consumer decides not to consume the first good. All right, so I want to leave this as an exercise. If you solve this one using Lagrange multiplier, then you may end up with a negative demand. So now you have to examine the corner solution. Okay. All right. And then let me quickly talk about the properties of the indirect utility function. Okay, so we talked about Walrasian demand. Okay, and if we substitute Walrasian demand into the utility function, okay, so X star is the optimal bundle. So U of X star is the level of utility from the optimal bundle. So can be interpreted as the highest level of utility. Highest level of utility obtainable given price vector P and W, income. All right. So that has a special name. We call that indirect utility function. Okay, and because X star depends on P and W, undoubtedly function V, indirect utility function, also depends P and W. Once again, its interpretation is, so function V gives us, informs us of the highest level of utility the consumer can attain given price vector P and the consumer's income W. All right. So let me show you one example. In case of Cobb-Douglas, the standard form of Cobb-Douglas is x1 to the alpha times x2 to the power 1 minus alpha, okay, in case of two goods. But utility representation has an ordinal property, ordinal property, right? So it does not matter whether we take a natural logarithm here, yeah, so still represents the same preference because natural logarithm is an increasing function. So after taking this ln, the function becomes this one. It becomes linear with respect to, natural logarithm. So alpha ln x1 plus 1 minus alpha ln x2. All right. So with this transformed utility, we can easily find out the Walrasian demand, from the Lagrange multiplier. So it has a nice property. So Cobb-Douglas has a nice property. Walrasian demand is going to be alpha times W over P1. That is a demand for good 1. And demand for good 2, 1 minus alpha times W over P2. So the way to interpret is, because the consumer puts weight alpha on the demand for good 1, and weight 1 minus alpha on the demand for good 2. Okay? So eventually the consumer will take the portion alpha of his income, and that will be spent on good 1. Okay? And the other portion, 1 minus alpha of the income, will be spent on good 2. Okay? Because the good 1 is traded at price of P1, good 2 is traded at price of P2. So the consumer can purchase this amount of units, this amount of good 1 and this amount of good 2. All right? So substituting this Walrasian demand into the original function, we obtain our indirect utility function. Function v is going to be alpha ln x1 star and 1 minus alpha ln x2 star. Okay, so after substitution, now function v depends on price factor P1 and P2 and income W. All right, and then finally, we have some properties of this indirect utility function. So the function v, it's a typo, it should be small v. Function v is decreasing in price. That's quite intuitive, right? There's nothing to prove. If in case of inflation, so if the price factor rises, so if the price rises, the consumer is naturally, the consumer becomes naturally, worse off, right? So the highest level of utility is decreasing, right? So because this budget set will shrink as P increases, right? So that means the set of affordable bundles will shrink. Okay, he has a smaller set of alternatives. So the highest level of utility, given that shrink the budget set, will get smaller than before. And second, the indirect utility function is increasing in income. Right, this is also pretty straightforward. Now the budget set expands as income increases. So with a expanded set, consumer can effectively increase the level of utility. So the function v is strictly increasing. And the third property, homogeneity of degree 0 in the price factor and W, it comes from the fact that Walrasian demand is also homogeneous of degree 0. Okay, remember function v is defined as u of Walrasian demand. Okay, and then we multiply alpha to P and W, and this becomes u of x star of P and alpha P and alpha W. Okay, and because x star is homogeneous of degree 0, x star is homogeneous of degree 0. All right, so it is the same as u of x star of P and W. That is, it brings us back to the the original indirect utility function. Okay, so function v is homogeneous of degree 0. Even after scaling up p and w by alpha, okay, we go back to the original function, all right? And then finally, quasi-convex. So, we say one function is quasi-concave, its upper contour set is convex, okay? And its counterpart is quasi-convexity. So now its lower contour set is convex. So think about this function defined on single variable x, function v, okay? It's lower contour set. So we draw one horizontal line, figuring out where this function takes a lower value than this level. So this is a level k, okay? Then we can see that function takes a lower value than k over this interval, okay? So that is a lower contour set of this function. One lower contour set with the level k of this function f. So this is a set of x such that function f takes the lower value. So it takes a smaller value or equal to, so it's a smaller than or equal to k. All right, and that is a convex if the function is quasi-convex like this. Okay, so its geometric interpretation is it has just at most single value like this. Okay, quasi-concave function, it has at most one single peak. Okay, and quasi-convex, it has a single value like this. Yeah, and then let me prove this statement in the live lecture next week, because we are going to discuss one exercise in the problem set I gave you previous week, and using one fact in that exercise, we can easily prove this quasi-convexity. Also, I'm going to illustrate the economic implication of this quasi-convexity in the live lecture as well. All right, so I'm sorry about the length of this video. I tried to cut down at around 30 minutes, but it's way longer than 30 minutes. But hope you enjoyed this video. I explained the how to solve. In this video I explained how to solve utility maximization and the properties of Lagrangian demand and properties of the value function indirect utility function. All right, now I continue to record the second video.